At the end of the previous video in this series, we saw that since realistic models of computation are polynomially equivalent and encoding schemes are also polynomially equivalent, we can define the classes P and NP independently of the specific encoding or machine model. So, P is the class of decision problem solvable by a deterministic polynomial time algorithm, while NP is the class of decision problems solvable by a non-deterministic polynomial time algorithm. Now, the time has come to establish the relationship between class P and NP. I hope you remember that we associate a guess module with a deterministic Turing machine to make it a non-deterministic Turing machine. After guessing a solution in the guessing stage, the algorithm proceeds to the checking stage, which runs as a deterministic polynomial time algorithm. Now, suppose we have a problem P that belongs to class P, meaning there exists deterministic polynomial time algorithm A that solves it. In a non-deterministic Turing machine, we can simply skip the guessing stage and implement algorithm A directly in the checking stage. This results in a non-deterministic polynomial time algorithm for the same problem. So, every problem that can be solved in class P can also be solved in class NP by just ignoring the guessing part. That's why we say class P is a subset of class NP. So now we know that class P is a subset of class NP. But what are the other possible relationships between P and NP? One possibility is that P is equal to NP, and the other is that P is not equal to NP. If P is not equal to NP, then P is a proper subset of NP. However, these are still open questions in computer science. The idea that P is not equal to NP, that is, P is a proper subset of NP, seems more convincing because a non-deterministic Turing machine appears more powerful than a deterministic Turing machine because it can solve certain problems much more efficiently. However, it cannot solve problems that a deterministic Turing machine cannot. It can only solve them faster in the theoretical model. There are many problems, such as the traveling salesman problem, subset sum problem, and the 0 1 knapsack problem, that belong to NP. For these problems, polynomial time verification algorithms exist, but no polynomial time algorithm is known that can actually solve them. Though there is no formal proof that P is not equal to NP based on the extensive efforts of mathematicians over the years, many believe that P is not equal to NP. And if this assumption holds true, it implies a clear distinction between the problems in class P and those in NP minus P. If P is not equal to NP, we can say that problems in class P are efficiently solvable, while problems in NP but not in P, that is NP minus P, are intractable. However, since there is still no definitive proof that P not equals to NP, the theory of NP completeness was introduced to better understand and classify the hardest problems within NP. Suppose we find a problem in NP which is at least as hard as any other problem in NP. This problem is known as NP-complete problem. Many NP-complete problems are known. An NP-complete problem is considered a hard problem, and for many years, mathematicians and computer scientists did not find efficient algorithms for NP-complete problems. Therefore, many believe that P is not equals to NP. Now, many questions may arise in the mind. Let us say a problem Q, which is an NP problem, is an NP-complete problem. But to prove that Q is an NP-complete problem, we have to prove that Q is at least as hard as any other problem in NP. This relationship based on the hardness can be established by a concept of polynomial reducibility. Let us say we have two decision problems P and Q. We use a set of symbols to encode them. For each problem, there is a set of strings that represent the yes instances. These are called LP for problem P and LQ for problem Q. Now, suppose there exists a deterministic Turing machine that computes a function f, and for all inputs x belonging to sigma 1 star, it satisfies x is element of LP if and only if fx is element of LQ. This means that LP is polynomial time reducible to LQ, which in turn implies that problem P is polynomial time reducible to problem Q. In simple words, we say that a decision problem P is reducible to another decision problem Q in polynomial time if there exists a function f that transforms any instance of P into an instance of Q in polynomial time, such that the answer is preserved in the transformation. This polynomial time reduction establishes that decision problem Q is at least as hard as decision problem P. Here, it is easy to understand that if Q belongs to class P, then it implies that P belongs to class P. However, if P is hard, then Q is also hard. Furthermore, we can easily establish the following. If P is polynomial time reducible to Q and Q is polynomial time reducible to another decision problem R, then P is polynomial time reducible to R. This is known as the transitive property of polynomial time reductions. Let's now try to understand the intuition behind these properties. When we say P is polynomial time reducible to Q, it means every instance of P is transformed into an instance of Q. Now imagine the set of all instances of problem P that are transformed into a subset of instances of Q. Let's call this subset QP. However, there might be other instances of Q that are not related to P. We represent these remaining instances as Qn. Just keep these two subsets, Qp and Qn, in mind. Now let's talk about the first property. Problem Q is at least as hard as problem P. Since all instances of problem P are transformed into some instances of problem Q, and Q may have additional instances in Qn, we cannot comment on the difficulty of the full problem Q, especially on the instances in Qn. That's why we say Q is at least as hard as P. It might be harder depending on how hard the Qn instances are. Now let's discuss the second property. If P is hard, then Q is hard. The reasoning is similar. If P is hard to solve, then the associated instances in QP are also hard to solve, which implies that Q must be hard as well. Now you might ask, can we say if Q is hard then P is hard? The answer is no. Why? Because we did not reduce instances of Q into P, so we cannot make any claims about the complexity of P based on Q. Next, let's look at the third property. If Q belongs to class P, then P belongs to class P. Since we can solve all instances of problem Q in polynomial time and we can transform each instance of P into an instance of Q, it means we can also solve problem P in polynomial time. We simply take an instance of P, reduce it to Q using the reduction function, and then apply the polynomial time algorithm for Q to get the answer. But now, can we say if P belongs to class P, then Q also belongs to class P? The answer is no, because we are not reducing instances of Q into P. We only reduced P to Q, so we cannot draw any conclusions about Q's complexity from P's. Now we understand that if a problem P is polynomial time reducible to Q, then Q is at least as hard as P. This concept can be used as a powerful tool. A few minutes ago, we said that a problem Q, which belongs to NP, is also an NP-complete problem if we can prove that it is at least as hard as every other problem in NP, right? Now we have the tool to do this job. We must demonstrate that every other problem in NP is polynomial time reducible to Q. If we are able to successfully perform this reduction, it means that Q is at least as hard as every problem in NP, and therefore Q is an NP-complete problem. Before we go further, we need to understand what it means when we say a problem is an NP-class problem. We associate a guess module with a deterministic Turing machine to make it a non-deterministic Turing machine. After guessing the solution in the guessing stage, the algorithm moves into the checking stage. The guessing stage is like a magical component that supplies a possible solution to the checking stage, and the checking stage verifies whether this solution is correct using a polynomial time deterministic algorithm. A class of problems for which both these stages, guessing and checking, work together to design a solution is known as NP class problems. On the other hand, When we ignore the guess stage and design a solution using only deterministic steps, such problems are known as P-class problems. Since for P-class problems, we ignore the guess stage and the checking stage is common in both classes, we can conclude that P-class problems are a subset of NP-class problems. Therefore, a problem Q is an NP-class problem if its solution can be verified in polynomial time. In other words, if a polynomial time verification algorithm exists for a decision problem, then that problem belongs to the NP class. Can we say that if a decision problem Q belongs to the NP class, then the problem is hard to solve? The answer is no. Why? Because P class problems are also NP problems, and we know that polynomial time algorithms exist for problems in P. So, if a problem belongs to NP, we cannot automatically conclude whether it is hard to solve. However, if we can demonstrate that every other problem in NP is polynomial time reducible to Q, then that means Q is at least as hard as any other problem in NP. If all NP problems are polynomial time reducible to Q, then Q is an NP hard problem. If Q is also an NP problem, that is, a polynomial time verification algorithm exists, then Q is an NP complete problem. A decision problem Q is NP-complete if it satisfies two conditions. First, Q belongs to the class of NP problems. This simply means that Q is a problem whose solution can be verified in polynomial time. Second, all problems in the NP class are polynomial time reducible to Q. In simpler terms, a problem P is NP-complete if it is in NP and at least as hard as any other problem in NP. The first condition is usually straightforward to prove. We just need to design a verification algorithm that evaluates the proposed solution in polynomial time. However, the second condition is tricky. Demonstrating reducibility from every NP problem to Q can be extremely time consuming and difficult, but there is a trick. Suppose we have a decision problem R which is already known to be NP complete or NP hard. This means that someone has already done the work to prove that all NP problems are polynomial time reducible to R. Now, if we can prove that R is a polynomial time reducible to Q, then using the transitive property which we discussed earlier, we know since all NP problems are reducible to R and R is reducible to Q, then all NP problems are reducible to Q. This proves that Q is an NP-hard problem. Now, if Q is also in the NP class, in other words, if a polynomial time verification algorithm exists, then Q becomes an NP-complete problem. So, what's the trick to proving that a decision problem Q is NP-complete? We need to find a decision problem R which is already known to be an NP-complete or NP-hard problem. Then we demonstrate that R is polynomial time reducible to Q. In other words, instead of reducing all NP problems to Q, reducing just one known NP-complete or NP-hard problem to Q is enough. And finally, we show that Q is in NP, that is, we provide a polynomial time verification algorithm. So, to wrap it up, proving that a problem is NP complete may seem daunting at first, but with the right approach, it becomes a structured process. First, you show that the problem is in NP, meaning its solution can be verified in polynomial time. Second, instead of reducing all NP problems to your problem directly, you reduce a known NP complete or NP hard problem to it using a polynomial time reduction. This elegant shortcut, based on the transitive property, makes the task both feasible and powerful. With the knowledge of P, NP, and NP complete, you can reason that a problem is not be proofly intractable, but it is believed to be so. In this video, we explored the relationship between P and NP. We also introduced the concept of NP complete problems and discussed how to prove that a problem is NP complete or computationally hard. In the next and final episode of this series, we will go full circle. We will take the problem we started with in part 1 and uncover why it's actually an NP complete problem. Don't miss it. This is where everything comes together. Thanks for watching. Don't forget to like, share, and subscribe so you never miss what's coming next.